Good morning, students. Today we are going to see the chemometric models. This is coming under covering the unit 1, but is an extra portion which need to be explained. Okay, which need to be explained. Very important topic, chemometric models. Chemometric models apply statistical, mathematical, and machine learning techniques to extract useful information from chemical data. These models helps in process monitoring, quality control, optimization, and predictive analysis in chemical engineering. Any models obviously to understand the relationship between the dependent variables and independent variables, and also it will help you to optimize the process. This particular chemometric models apply machine learning techniques to extract the useful information from chemical data. So there are some 7 steps which are available in chemometric modeling. First one is objective. The second one is data collection. Third one is data pre-processing. Fourth one, model selection. Step 5 is model training and validation. Step 6, model deployment and interpretation. Step 7, continuous monitoring and improvement. So there are some 7 steps which will help you to understand the chemometric modeling and the way we need to process this type of modeling. Okay, so for the optimization of the process. So that's supposed to be very clear. Students supposed to be very clear on that. So objective. Before developing a chemometric model, it is essential to define the purpose. What for we are doing this model. Okay. So common objective in chemical engineering include first point, predicting product quality based on process parameters, analyzing the complex spectroscopic data. After we obtain the data from the instrumental analysis by using a sophisticated instruments, okay, how to analyze the data? For example, in XRD, X-ray diffraction, if we have a short peak that represent the crystallinity, and also it talks about the structure, the component structure. The structure of the component can be determined, and the atomic how the atoms are arranged. Okay, that can be visualized. Okay, so analyzing the complex spectroscopic data, that is one of the objectives actually for the chemical engineers. Monitoring the chemical process variation and optimizing the process condition. So most of the cases we will try to optimize the process. Okay, there are some times we need to collect the data from the analytical data from spectroscopic data. We need to analyze and come to the conclusion. So in that case also we can go for a chemometric modeling. The common objectives are predicting the product quality based on the process parameters. That is also very important. Product quality based on the process parameters. Which one is more relevant? So the dependent variables and the independent variables, how it has been correlated. Is there any significant effect is there or not? Predicting the product quality based on the process parameters. Okay, some of the parameters there is no much effect. So varying the parameters doesn't make any sense. Analyzing the complex spectroscopic data, monitoring the chemical process variation, and also optimizing the process condition. So the very good example here is, it has been given here, predicting the concentration of chemical species in a reactor based on the temperature and flow rate. So let's say A plus B gives C. I want to find the product concentration C in a CSTR. Okay, so the concentration of chemical species in a reactor, when I change the temperature, pressure and flow rate, how it has been changing. Okay, or whether my product formation is large or is getting reduced. Okay, so that's what the main objective is supposed to be for any chemical engineer, to understand the effect of process variables on the reaction yield, especially inside the reactor. The second point is data collection. Gather chemical process data from experiments, sensors or historical records. So a lot of sensors are available, like even pH meters, okay, temperature sensors, carbon dioxide sensors. Okay, so a lot of sensors which are available to determine the composition. Okay, chemical process data from experiments or by means of sensors or historical data. So the data may include spectroscopic data, or it may be a chromatographic data like HPLC, GC, high performance liquid chromatography, gas chromatography, even GCMS, gas chromatography, mass spectroscopy, process variables. Okay, so in GCMS, the data it auto check with the library function which are available in the GCMS. Okay, it will automatically will help you to determine the the compound composition. Okay, so chromatographic data which will help you like from HPLC and GC. Okay, if you give to this model, that will help you to predict the composition for the complex in nature. Okay, process variables like temperature, pressure, pH, flow rate, this all need to be collected. Data is supposed to be collected. So collecting Raman spectroscopy data to determine the composition of a polymerization reaction mixture. Let's imagine a polymerization reaction is carried out in a CSTR. Okay, I want to collect the Raman spectroscopy data. What is Raman spectroscopy? It's a powerful analytical technique used to study the molecular vibration, providing information about molecular structure, composition, and their interaction. So the molecular interaction, okay, as well as the molecular structure and composition can be determined by Raman spectroscopy. That particular data will help you to determine the composition of polymerization reaction mixture. Data pre-processing. So the data pre-processing will be noise level. For example, I am taking a video to in order to show to the students who are those who are taking a honors and minors course under blended learning. Okay, so in that case, if the noise is there, for example, I just have a fan. Okay, so that noise, or even the air conditioners nowadays, even some air conditioner may give noise. Okay, so are we sitting away from this particular noise? So in order to have a good quality of videos, okay, now that I need to think of. Similarly, data pre-processing, the raw data may have noise, missing values, or outliers. Outliers are deviation from the certain common data, like outliers, deviation, anomaly. And pre-processing techniques include normalization or standardization, outlier detection, dimensionality reduction, scaling variables to ensure uniformity, and outlier detection, removing erroneous data points. So if there is any data which has been coming out from the outliers, anomaly away from the data, common data, so removing erroneous data, that means deviating from a very high deviation. Okay, that type of data can be skewed off or can be taken off. Okay, so the dimensionality reduction using principal component analysis is a statistical technique used for dimensionality reduction. Usually, this word dimensionality reduction used in the machine learning subjects. Okay, so dimensionality reduction is nothing but reduce the number of variables. Okay, so using principal component analysis to reduce the redundant data, that is dimensionality reduction. Okay, as well as what you call it, reduce the number of variables which is not have much effect. Okay, so the dimensionality reduction in data processing using PCA to reduce the redundant data. So redundant data. Okay, so which has been repeating. Okay, so standardization sensor readings from a distillation column before analysis. So we need to make sure this sensor is working properly or not. That we need to make sure. So standardization is very important. So when you go for data pre-processing, so what type of standardization of any of the equipment or the process supposed to be carried out? Okay, whether it's working correctly or not. Okay, this is one of the questions which has been raised in the recent interview where I went to the eminent university. Okay, so they asked me how do you make sure the sensors is working properly, and also before that question they asked what is the difference between precision and accuracy. So these are all things supposed to be you as an undergraduate student supposed to be aware of it to have a deep knowledge on a particular subject. Okay, so sensors, when you, for example, the same question I'm asking you, how do you make sure the sensor is working properly? So I can have a benchmark. Okay, I have another sensor and then make sure that it is showing the same results. And the another question they have raised also, they arise as how this both sensors are working. If the both sensor is not working, how do you make sure the sensor reading is correct? Then we will go for the experimental analysis, that is a technical analysis. Okay, so for that particular compound what the sensor is determining, okay, determining, right? So we should be very careful on this type of what you call understanding the subject. Okay, so that is very important. And coming to the third point of fourth point of the chemometric modeling, chemometric models can be statistical or machine learning based. Okay, so it need not be necessarily a statistical mathematical thing, it also machine learning. So the principal component analysis, partial least square regression, multiple linear regression, and artificial neural networks also is used in what you call this analysis, regression analysis is available in statistical and also the machine learning like artificial neural networks. Okay, so this will help you to identify which model we need to select. Okay, so for example, for our case, using a process partial component analysis to analyze the fermentation process variation based on the multiple input variables. So example here given is the fermentation process variation based on the multiple input variables. So there are plenty of input variables varying. So in that case, we will go for a PCA, process component analysis, used for pattern recognition and data visualization. So what is the main purpose of PLSR? That is a partial least square regression, predict the chemical properties from spectral data. Multiple linear regression, model relationship between the multiple input and output variables, that is a dependent and independent variables. Artificial neural network captures complex nonlinear relationship. Most of the reactors, all the chemical engineering equations, most of them come under the nonlinear equations. Okay, either it may be a logarithmic or exponential or quadratic, okay, or polynomial. Okay, so you know already. So captures complex nonlinear relationship. Okay, is a common model. Artificial neural network is a common model. Okay, so model training and validation. How do you model the? How do you train the system? Okay, divide the data set into training and then testing subset. So training means, for example, you have 100 data, just give almost 80% of the data for training and then testing the 20%. Okay, so train the model using statistical techniques or machine learning algorithm. Validate the model using the cross validation methods. Okay, so that is very important. So training a PLSR, partial least square regression model, to predict drug concentration from UV spectroscopic data and validating it using a leave one out class validation. So we are going to train the PLSR model, that is a partial least square regression model, to predict the drug concentration from UV spectroscopic data. So let's say I want to know how much is the drug concentration. So by using the UV spectroscopy data, okay, you will have a what you call particular wavelength. It will give you a peak, right? So absorption value or transmittance value will be given obtained by the UV spectroscopy. So with that data, we can predict the drug concentration. As the transmitted absorbance value is higher, obviously what the concentration will be higher, and so on and so forth, right? So value at a particular common wavelength. Okay, that you know already. That you even for elemental analysis in wastewater or water sample, we will try to find how much is the calcium, magnesium, component analysis, right? So the drug concentration by using UV spectroscopy data will help you to understand how much is the drug concentration by using the PLSR model, for which the data which has been obtained has been used for training, and some of the data, that is 20% of the data, has been used for the testing the model. So here they are using a leave one out cross validation model. What is leave one out cross validation? Even I have learned today this leave one out cross validation model is a technique where the data set with the n sample is split into n minus 1 samples. So the training test set supposed to be n minus 1 and test set supposed to be 1 sample. Okay, so model deployment and interpretation. Apply the trained model to new data for real-time prediction. Interpret the model output to make informed engineering decision. Very important. Model deployment and interpretation. So once you deploy the model, let's say you have a chemometric model. In the chemometric model, you have chosen the partial least square regression where you have a data of spectroscopic data. Okay, and then you just try to find the drug concentration. Apply the trained model to new data for real-time prediction. So that is a sixth step: model deployment and interpretation. Interpret the model output to make the informed engineering decision. So at a real-time scenario, once you get the data, once you obtain the spectroscopic data, immediately you could be able to identify the system. Okay, so and then you can proactively do some measures. And deploying an artificial neural network based chemometric model in a chemical plant to monitor and predict the polymer properties during production. So artificial neural network based chemometric model is to monitor and predict the polymer properties during the production. So let's say you have a reactor CSTR and polymerization reaction takes place. You have temperature, pressure, that variables need to be varied, and you just try to find the variation and then try to accordingly you could be able to get the results. Okay, so you could be able to predict the thing. Okay, so artificial neural network based chemometric model in a to monitor and predict the polymer properties. Coming to the last part, continuous monitoring and improvement. Let's say this is a final step. Even outcome based education, what we say as a lecturer, as a educationalist, we say actually is any process. It need not be only a education or anything. Continual quality improvement is must. Even if you go for industry, even they have a plan. Okay, so we need to go beyond maximum effort. That means, and then we need to try to avoid the lack. Okay, so continuous quality improvement. So continuous monitoring and improvement is very important. Actually, it's the last step of the chemometric modeling. Update the model periodically with the new data. So you have trained the data with certain data or previous data which are available or the current data, and the future data also need to be uploaded to the system and then train the system. Okay, with the new data, recalibrate if process conditions change, and then if you have a process condition variability is there, changes is there, you need to recalibrate the model. Improve, that is a machine learning algorithm or the model need to be updated. Improve the model accuracy by integrating the additional variables or advanced algorithms. So the example here is refining a soft sensor model in a petrochemical refinery to predict the crude oil quality based on the updated sensor data. Okay, so they need to update the sensor data and then try to find the refining a soft sensor model by using the in a petrochemical refinery. Okay, in a petrochemical refinery. And coming to the chemical engineering application of chemometric models, quality control in pharmaceuticals, process optimization in chemical plant, environmental monitoring, petroleum refining, and food and beverage industry. So coming to the first part, quality control in pharmaceutical, partial least square regression models analyze spectroscopic data to ensure the drug formulation. So it's an example, this particular model for this particular case, pharmaceutical companies. Okay, artificial neural network models optimize the reactor condition for maximum yield. So whenever you have a non-linear equation, okay, then we go for an artificial neural network models that will respond very accurately. That will be helpful in the process optimization. Environmental engineering, partial component analysis. So helps in analyzing the air or water pollution data. And petroleum refining, chemometric models predict the fuel properties from crude oil composition. Food and beverage industry, spectroscopic chemometric models ensure the product consistency. So chemometric models helps in optimizing and monitoring the reactor performance by analyzing the multivariate data from sensor and experiments. In this study, we apply partial least square regression to predict conversion efficiency in a chemical reactor based on the process variables. So now we are going to see a case study regarding the chemometric models, which will help in optimizing and monitoring the reactor performance. So in this study, what we are going to apply? We are going to apply the partial least square regression to predict the conversion efficiency in a chemical reactor. So in the last case, we have seen the polymerization reaction carried out and try to find the efficiency by changing the variables, right? Similarly, we are going to see over here. Okay, so what is the problem statement here? So let's say assume a continuous CSTR, okay, for our case study, continuous stirred tank reactor used for a polymerization reaction, and the variables, that is dependent variables and independent variables, are temperature, pressure, residence time, catalyst concentration and agitator speed, and their corresponding unit has been given. For temperature is degree Celsius, for pressure bar, for residence time is a time frame is a minutes, for catalyst concentration mole per liter, for agitator speed in revolution per minute RPM. Okay, so what is the dependent variable? The dependent variable is a conversion, reactor conversion. So using chemometric modeling under a partial least square regression model, okay, the goal is to predict the conversion efficiency and optimize the reactor condition. So what we need to do? The next step, data collection. So data collection is varying a different temperature and pressure and time frame and catalyst concentration speed. What is the conversion? The last one is the dependent variable, that is the yield conversion efficiency. So in this case, data pre-processing, standardizing variables, mean is equal to 0, variance is equal to 1, handled missing values with mean imputation, applied principal component analysis to remove the redundant information. Okay, principal component analysis for the redundant information, same redundant data or redundant information. Okay, so that will help you to reduce the noise level. So I can say it is a noise level. Okay, because if the system is not standardized, that means that error will accumulate and will be reflected in the model as well. So while collecting the data from the system or from the process, you should be very careful whether that is a standard data. Otherwise, the small change in the data will affect the output response. That we need to keep in mind. And coming to the chemometric model using the partial least square regression. Partial least square regression is chosen as it handles a collinear variable and reduces the dimensionality. So here the reduces dimensionality talks about the reduction in the number of variables. Okay, so 80% data used for training and 20% for validation. Model equation comes with the temperature x pressure, x time, x catalyst, and x speed. Is a multivariable. Okay, is a multivariate analysis coming under. Okay, so the model equation, but is coming under a partial least square regression because it handles the collinear variables as well as the reduces the dimensionality. So model performance and results. So when it shows R square is equal to 0.92, that means a strong predictive power. If a root mean square error is 1.8 is a good accuracy. Importance of variables based on the model coefficient. Okay, so for example, whether the system is significant or not, whether the variable is significant on the process response, okay, on the response variable, that we need to check. So the catalyst concentration is most significant. Temperature and pressure are moderately significant. That means if you change the temperature and pressure, that will not give you a better highest yield. But when you change a small change in concentration, will give you a more effect on the response variable. That is your concentration. That is your efficiency of the reaction or the yield of the reaction or the concentration of the product. Okay, so the least significant is on residence time and agitator speed. So there is no much significantly different. There is no much significant difference has been found when you try to change the agitator speed very high or low, or residence time is minimum or maximum. Okay, because this is coming under the CSTR. So the principle behind the CSTR is what do we say actually? At any period of time, the concentration inside the reactor is equal to the concentration outside the reactor. But the residence time talks about how much time the fluid element has been spent inside the reactor. That you know already. So the residence time, if the fluid has been spent much time or even by shortcut it leaves the system, okay, doesn't have much effect on the product formation. That you need to understand. So that's why I say is a least significant. And coming to the sixth case, so the sixth one, the reactor optimization and insight. So the catalyst concentration varies from 0.02 to 0.03. The improved conversion by 5%. So when it varies from 0.02 to 0.03, improved conversion by 5%. Operating at 90 to 95 degrees Celsius provided optimal conversion with minimal side reaction. So sometimes the reaction will not proceed when you have a temperature effect because of the temperature is high. It will give you what you call the unparalleled reaction, or it may give you unwanted byproduct reaction. Okay, so that you need to keep in mind. Reducing the agitator speed at negligible impact, helping in energy saving. So this case study demonstrates how chemometric models help in reactor performance prediction and optimization. By analyzing the multivariate data, that is a temperature, multivariate data. Chemical engineers can fine tune the process condition, maximize the efficiency, and reduce the operational cost. So multivariate data. So what are the multivariate data? The multivariate compound, that is temperature. I mean the independent variables, multivariate independent variables, right? Temperature, pressure, concentration, catalyst concentration, and so on and so forth. Okay. So the conclusion of today's lecture regarding the chemometric models, very important in chemical engineering perspective. The chemometric models are powerful tools in chemical engineering, providing insights into complex data, optimizing the process, and ensuring the product quality. By allowing the structured approach, data collection, pre-processing, model selection, training validation, and deployment, engineers can harness chemometrics for better decision making. So, what we are doing this model? Without doing the experiments, okay, we could able to predict with the data which are available and train the system and try to find it out the. So if we obtain this particular data, what would be the predictive output, okay, without doing the experiment itself. So please try to understand the importance of chemometric models in engineering, so that will help you to optimize the process, okay, very important point. And it will train the data, okay, so complex data can be easily analyzed and ensure the product quality. So this is what I would like to cover in today's lecture. This is a last part of the unit one. Okay, this is coming under, it's not coming under the content, I mean the syllabus, but however I just would like to add on a, additional material to understand the different types of models. Okay, either by using a statistical method or by means of a machine learning algorithm. Okay, so in third unit we are going to see what is machine learning algorithm. Until that, it just please be tuned with the thing. Okay, all the best for your what you call part one, which is going to be held, I believe, that on 20 and 21st. Okay, so the first two units I have already covered. If any of the content which is you have any doubt on thing, and if you request me to add on some of the videos regarding some topics, I'm ready to do the same. Okay, keep in touch. Have a good day.